Okay, so welcome back to the lecture series, and it's the odd class just before the half of the entire course. So today I'll not go formal, I'll be doing some kind of a chit chats here and there. The central theme for today is that we have been making many assumptions, and what really happens if we do not make those assumptions. Like one of them was that the system is discrete. I'll still not say what happens if the systems are not discrete because modern AI is another course. But then we have been assuming, of course, that the system is deterministic. So if I move a block, I move exactly one block. So I don't go a little left, a little right, as well as we've still assumed it's fully observable. So I know exactly where I am. I know exactly what's the world around me. I know everything about the system. It's fully observable. So let's go one by one, and first let us see what happens if the system instead is not deterministic, it is stochastic in nature. Now, I'll still make the assumption that it is discrete, and because of which the stochasticity may appear to be a little odd than my examples given previously, but we're still gonna give it. That's my same old grid world. This is where I am at 2, 2, and from 2, 2, everybody knows if I take the action right, I go to, of course, a 3, 2. However, now what really happens is that the system is stochastic. So instead of a 3, 2, I could end up at a 2, 3. This is what happens if my one of the leg is not really correct. I'm too drunk, so only one leg or only one wheel is actually working. I could even do it the other way around. I could say it goes at 2, 1. Maybe the other leg or the other wheel is not working. So for a stochastic system that we are now dealing with, I don't have one action, I have multiple actions which are possible. So previously we said that from state S, if I apply the action A, I just get one state S dash. This is when it is deterministic. However, in a stochastic world, from a state S, if I apply an action A, I get not one, but a set of possible future states. And that's a problem that I'm gonna informally look at today. Now, we've seen this before in a topic called as adversarial search or game tree. And in an adversarial search or game tree, we can model for both stochasticity as well as taking actions by a one player game called as max with chance nodes. So this problem can also be called as game playing with God. You take the max nodes and max actions, God takes the chance nodes and the chance actions. Now, of course, if that was the only case, it was simple for me, but notice around here we have cycles. From 2, 2, I can go to 3, 2, I can go to 4, 2, I can go to 4, 1, I can go to 3, 1, and I can again go to 3, 2. They are cycles, which means my game tree is infinite, and we know that that's not really a problem because you can cut it off at some depth and take utility. The other difference is there is no utility over here. There are costs that I would like to minimize. They behave, let us say, pretty similarly. So if I have to model this thing using what we studied, I'll say this, let us say, is S, this is S dash, and this is A. It could be very conveniently modeled as at S, I will take an action out of multiple, one of them is A, then God plays with multiple outcomes. I control this one, God controls this one, and it's simple. Which, of course, one of the actions gives is S dash. Now, previously, when we were doing this, maximum we could go upon is a few depths, 4, 5, because exponential complexity trees grow very fast. And we could still do that because the games are made with a lot of expertise so as to be fair. And because of that, they are good moves, they are chances, there are so many things that we used. Now I'm talking about an altogether general problem, and one difference that I will now inject is that because I'm solving any general problem, now my question is not that can I beat the opponent who is maybe a better player. My question is altogether different. Is there even a valid solution that takes me towards the goal no matter how God plays? God may be very cunning to me. I'll teach this guy a lesson and may act as an adversary and may, at God's moves, select in actions which are select in states which are extremely bad for me. However, all that I need to find out now is there a solution? And then, of course, if I can get an optimal solution, that would be the best. And therefore, now what I'll not do is what I was doing in game search, which is just to think ahead 2, 3 moves, make a move, and then I'll care about the rest. In such a case, for a generic problem, you might take moves, end up in a situation where you get trapped. There is no solution as well. So I'm going to do a famous thing in AI. I cannot solve an infinite depth tree in full. I don't have the computational resources for that. It's not feasible. And therefore, I will buy a solution at the cost of optimality. So let's park optimality for now. Of course, as I go upon, you can think of multiple heuristics when you practically solve problem. You can think about heuristics which give you some optimality, but formal way of dealing is I park the optimality aside. I say that, okay, if there is a solution, I will find it out. It may or may not be the best. And once we do that, I give in new names to these little things in the game tree, and my new names will be called, instead of a max chance, as a and node and a or node, and the names have meanings. So And node is the one which is played by God. That's also how we denote it. So the name goes like this. I just need a solution. I just need one solution. However, I don't know what will God do. I do not know what move will God make. I have absolutely no idea of it. And because I have absolutely no idea of it, I instead would probably like to solve all of them. So, examinations, you do not know which questions will come. You solve for all of them. Only when I give you a question paper, you see this I've studied. I already have a solution for it. So I don't know what will God make, what branch will God select. So I'll solve for all branches. Once I solve for all branches, then whatever God does, I have a solution. However, talking about the all nodes, I just need to get one solution. Which branch do I select? That's in my hand. I select the branch, and because I select the branch, if I get a solution out at this branch, it gives me a solution. I say, I don't care about the other branches. On the other hand, if this branch says there is no solution, and I get the solution at this branch, I say, hey, I'm happy with it. I just had to get one solution, good or bad. I don't use these branches. I just prune them out. I say, I wanted a solution. I already have that. The other difference that, of course, you can say is that there's a S associated with this. There's no SA, SB associated with this. There's finally a S dash associated with what is its children, because I don't know what's the state around over here. After my move, God is immediately playing a move to give me one of the possible S dash. And now let me represent what the solution will have a general architecture like. So the solution is, of course, not a path, because I do not know the moves of God. On the other hand, it is a strategy or a policy, which is for whatever God does, I know what it is. For whatever God does, I know what is the solution. So, suppose after thinking out, problem solving is of course recursive, that we now know. Suppose after a lot of computation, I say from 2, 3, which is here, down is a good action. From 3 to here, right is a good action. And from 2, 1 here, right is a good action. So technically my solution or my policy or my strategy is defined in the way as if God selects 2, 3, then I need to take down. If God selects 3, 2, then I need to take a right. If God selects 2, 1, then I need to take a right. Why did we not do this thing in adversarial search? You didn't look at this notation because everything was online. I look ahead 5 moves and I only decide one correct move. After making that move, I do a new search. Now everything is offline. Everything is happening in the head with no moves played. So I actually need to store the solution search policy. I just cannot say I need to store in one action immediately taken, and therefore I need the explicit storage of it. I've got my own notation of this. So I say policy at 2.3 is down, policy at 3.2 is right, and policy at 2.1 is right for the state that you are currently at. So that's from 2 if I take an action A, that is what happens. So if I reach through this step at 2.3, I need to go down, 3.2, I need to go right, and 2.1, I need to go right. In general, I will say pi of s dash is equal to a. That's just what I write. You can use whatever that you like. And this pi is, of course, in the most local state as you search in the current path.